Hello, class, and welcome to part 2 of the Unit 6 review. We were on example number 8, and we just finished part D. So we need to continue here with part E. This being to compare the results to those obtained in part A, right, where we saw that when we changed that level of confidence by increasing it, that would then expand our confidence interval. So by expanding the confidence interval, that means that margin of error increased. So the margin of error increased in our case. And then finally, if the sample size is 14, what conditions must be satisfied to compute the confidence interval? So for this one, the sample data must come from a population that is normally distributed with no outliers. So due to that sample size being small, it needs to be at least 30 in order for us to not have to worry about that. Well, I shouldn't say that. It needs to be at least 30 for us to be able to claim approximately normal. Question number 9. I have here, a nutritionist wants to determine how much time nationally people spend eating and drinking. Suppose that a random sample of 1,020 people aged 15 years of age and older. The mean amount of time spent eating and drinking per day is 1.72 hours and a standard deviation of 0.57 of an hour. And let us say a histogram of time spent eating and drinking each day is skewed right. Use this result to explain why a large sample size is needed to construct a confidence interval for the mean time spent eating and drinking each day. And when we say large, again, that means at least 30. This would be since the distribution of the time spent eating and drinking each day is not normally distributed. Why is that? It's because we were told it's skewed right? The sample must be large, again, at least 30, so that the distribution of the sample mean will be approximately normal, which we saw happen with that central limit theorem. For part B, in 2010, there were over 200 million people nationally aged 15 years of age or older. Explain why this, along with the fact that the data were obtained using a random sample, satisfies the requirements for constructing a confidence interval. This would be that let me bold this first, the sample size is less than 5% of the population size. Right, since let's face it, sample size of 1,020 is definitely less than 5% of 200 million. For part C, determine and interpret a 99% confidence interval for the mean amount of time Americans aged 15 years of age and older spend eating and drinking each day. So for this, we are going to need to hop into stat punch for this, and we are going to go to stat t-stats, one sample with summary. A mean was 1.72 hours. Sample standard deviation of 57/100th of an hour. Sample size. This was 1,020. We want confidence interval to be 99% confidence. So we are given this. Lower bound 1.6739. An upper bound of 1.7661. Let me just write that down, and then we can interpret it. All that fun stuff. So the lower bound, 1.6739, and the upper bound, 1.7661. So this is going to be the nutritionist is 99% confident that the mean amount of time spent eating and drinking, eating or drinking, I should say, gotta be consistent. Eating or drinking per day is between 1.6739 hours and 1.7661 hours in this case. And then finally, could the interval be used to estimate the mean amount of time a 9-year-old spends eating and drinking each day? Explain. No, it will not. The interval is about people age 15 or older, right? The mean amount of time spent eating or drinking per day for 9-year-olds may differ. So that would be a no, in essence, for that. Moving right along then. Question number 10. We have a data set. Ooh, fancy. The accompanying data represents the total travel tax in dollars of a 3-day business trip in 8 randomly selected cities. A normal probability plot suggests the data could come from a population that is normally distributed. A box plot indicates that there are no outliers. So based on this data set, we want to determine a point estimate for the population mean travel tax. So that's the data I've been having here on the screen. So to find our point estimate, we are going to go to stat, summary stats, columns. We're going to choose our one column, and we're going to compute the mean, which, as we could see on here, since this is money, this rounds to $83.14. So X bar is equal to $83.14. Part B wants to construct and interpret a 95% confidence interval for the mean tax paid for a 3-day business trip. So we are going to go to stat. T-stats, one sample with data this time. We have a data table. We're going to choose our one variable, and this was a 95% confidence. And we obtain this. The sample mean should match. The lower bound, $73.17. An upper bound of $93.10. So let me write that first. So lower bound would be $73.17, and the upper bound would be $93.10. So interpretation-wise for that, it's going to be what one can be 95.00%, and yes, they'll make you put in those decimals, confident that the mean travel tax for all cities is between $73.17 and $93.10. Part C wants to know, would you recommend to a researcher who wants to increase the precision of the interval, but does not have access to additional data? Which, let us face it, does unfortunately happen a lot. The researcher could decrease the level of confidence. So the researcher could decrease the level of confidence for this. And finally, the last question for this. A doctor wants to estimate the mean HDL cholesterol of all 20 to 29-year-old females. How many subjects are needed to estimate the mean HDL cholesterol within 4 points with 99% confidence? Assuming that sample standard deviation is 14.8 based on earlier studies. And let's say the same thing again with the 95% confidence. And then how does this decrease in confidence affect the sample size needed? So we are going to go to stat. Z stats, one sample with / sample size. The confidence level at first was 99%, sample standard deviation of 14.8. The width was 4 points times 2, so a total of 8. Sample size for 99% confidence is 91. But part B wanted us, well, I shouldn't say part B, but the next part of it wanted the confidence level decreased to 95%. I'll put this back to 8 for the width. The sample standard deviation stays at 14.8. That sample size drops down to 53. So for that 99% level of confidence, that used a sample size of 91. For the 95% level of confidence, that used a sample size of 53. So how does this decrease in confidence affect the sample size required? Well, we could see what happened, but decreasing the confidence level decreases the sample size needed. As we saw with the calculation. So that is it for this Unit 6 review. Let me know if you have any questions or concerns. Thank you.